All right, we have a magician that wants to know whether he could levitate a charged object of 1 kilogram by placing another negatively charged object on top, and we're going to charge both of them by friction. That would be a pretty cool trick. If you could hide this, then this would seem to be floating. All right, so this one will be negatively charged. I guess that's a pretty big sphere, but it doesn't say anything about its size, so I think we probably can assume that this is a point charge. So we'll assume that both this is going to be, I guess, if I want an attraction, probably this will have to be positive, if this one is negative. Because if I wanted this to suspend, the idea is there's going to be gravity down, and I need to somehow pull it up with electricity. So we can first going to assume they're both point charges, and then we're going to be using Coulomb's law, sorry. Okay, so that's the system. So they're not given any number, but I guess we have the distance here is 20 centimeter. So we're going to assume probably they can have the same charge on both, roughly. So we'll get Q on plastic minus Q on plastic, and then Q on the 1 kilogram object, and the question is what is Q so that this floats. Alright, so this is an equilibrium problem. This mass is not moving. I'm going to first always forces, let's draw a free body diagram. I have F gravity. This is a free body diagram on mass equal 1 kilogram. I'm going to have Fg, and if there's not in contact with anything, we're going to neglect drag. So then we just have the electric force upward. Okay. There's no acceleration. So the net force should be 0. That means that F electric should be equal to F gravity. Okay. Well, F capital G, actually. But, so we're near the surface of the Earth. So Fg is just m times g, and now I'm going to do a lot of just order of magnitude because I just want to know whether it's possible. So this is a 1 kilogram, this is roughly 10, so this is 10 Newton for this object. Alright, so what kind of electric force do we need to get, what kind of charge do we need to get 10 Newton? So the electric force this is Coulomb's law. So you see, here we're near the surface of the Earth, so I don't use the 1 over r square because that would be the radius of the Earth. For the nearest surface of the Earth, is just m times g, as we see in 211. But the electric force, there's no like shorthand like this. It's always the full Coulomb's law, which is this capital K. Then I'm going to get Q square, both charge square, and divided by the distance square, r square. So K is Coulomb's constant, which is roughly 9 times 10 to the 9 Newton meter square Coulomb square. For approximation purposes, is 10 times 10 to the 10, so 10 times 10 to the 9, which is going to be 10 to the 10, roughly. That's K. R is 20 centimeter, which is 0.2, which for approximation we'll take to be just 10 to the minus 1 meter. Alright, so I want this to be equal to 10, so what do? I just say, and I want to solve for Q, so I have K, Q square over R square equal 10, which means Q is equal to R square times 10 divided by K square root. So R is 10 to the minus 1, so this is 10 to the minus 2 times 10 divided by 10 to the 10 square root. So that's 10 to the minus 1. That'll be 10 to the minus 11. Square root is 10 to the minus 5.5. 11 divided by 2. That's Coulomb's. So that's the charge we need in order. So this magician will need to have a charge of 10 to the minus 6 Coulombs, roughly. And that seems like it's not that big of a number, 10 to the minus 6, but it is. It really is a huge number of charges. The Coulomb is a huge unit. 1 Coulomb is an insane amount of charge. We almost never have 1 Coulomb of charge on any object. So when we do friction, when we put friction here, we have 10 to the minus 8, 10 to the minus 9 coulomb. And this is still 10 to the 10 electrons. Because 1 electron has a charge of 10 to the minus 19 coulomb. So it's still a huge number of electrons. There's about as many electrons, extra electrons on this sphere as there are stars in the galaxies. Huge amount of electrons. But still very, very small charge. So yeah, so this would be a cool magic trick, but 10 to the minus 6 coulombs, you're never going to get that by friction. Alright, one thing the magician could do is maybe you could use a smaller mass. Instead of 1 kilogram, we could do something smaller. So I have this for now sign here. What kind of mass could we do? Well, if we did a milligram, say a little styrofoam ball of a mass of about 1 milligram, so that's 10 to the minus 3 gram, and a gram is 10 to the minus 3 kilogram. That's 10 to the minus 6 kilogram. Well, now, that means Fg on that, 10 to the minus 5 Newton. And now Q will be 10 to the minus 5 times 10 to the minus 2 divided by, let me just remember myself, 10 to the minus 2 divided by 10 to the 10. Square root of that. So that's square root of 10 to the minus 17. And now you're talking 10 minus 8.5 coulombs. That's exactly the kind of charge you get when you do friction between 10 to the minus 8 and 10 to the minus 9. 10 to the minus 8.5 should be roughly doable, and by friction. So you can levitate, but you need something like a milligram, so very small. And so that would not be a cool magical trick because nobody can see it. And it's even worse than that. If the magician actually tried this trick, he would have another problem. What happened if I put my little ball here, and this is now it's a 1 milligram ball, and I have a negatively charged object. This is my little ball. And so the F electric, I put it just at the point where F electric is equal to Fg. So this is an equilibrium. Everyone is happy. Let's say there's a little, somebody breathes and the air moves my little milligram ball a little up. So go up just a little bit because, I don't know, some reason there was a draft. If it goes up, then I'm closer, this positively charged ball is closer to this one, so the electric force is going to be bigger than gravity. And so if I get slightly closer, it's going to feel a force up, and it's therefore going to go even more closer. So this is unstable. If it goes up a little bit, it's going to quickly go towards that negative charge because it's going to have a net positive force. Similarly, if it randomly went down, you place the styrofoam ball and then just goes down a little bit. Well, if it goes down, the electric force will decrease while the gravity force will stay constant. And now it will have a net force downward. So this is called an unstable equilibrium. If you move it up or down, if you move it up, it will keep going up. If you move it down, it'll keep going down. So you're a magician, you put that styrofoam ball, if you don't put it exactly right, it will go up or down. And even if you put it exactly right, any little disturbance might make it move up or down. Okay? So it turns out that nice little trick really does not work for all sort of reasons.